Roshni, there are people in the waiting room, no?
So Gopi will be okay. I can admit them.
Yes, I'm reading the paper.
Okay, then shall we start now?
Roshni, we are on live.
Okay. Hello, everyone. Very warm welcome to all of you joining us online today. So we'll start the talk now. Today we have a Vigyan Adda lecture, and Pallavi, would you can you introduce the speaker? Uh,
Yeah. Good afternoon, everyone. I'm a faculty at ICTS, and it's a pleasure to welcome you all today and also introduce today's speaker, Professor Sendhil Raja S. Professor Sendhil Raja received his BSc degree in physics from PSG College of Arts and Science, Coimbatore in 1994. And after receiving his MSc degree in physics from IIT Madras in 96, he joined the Raja Ramanna Center for Advanced Technology to pursue a career in optical instrumentation. Then he received a PhD in physics from IIT Madras in 2009. And please note that he is a recipient of Young Technologist Award of the Department of Atomic Energy for the year 2006. As part of the LIGO scientific collaboration, he's also a recipient of the Special Breakthrough Prize in Fundamental Physics for the year 2016. And he currently heads the Advanced Lasers and Optics Division of the Lasers Group at Raja Ramanna Center for Advanced Technology, Indore. His expertise is in optical system design, optical instrumentation, and optical systems engineering. He is the project leader and project spokesperson for the LIGO India Project. With that, I welcome Professor Sendhil Raja. Over to you, Professor.
Thank you for the kind introduction. So let's dive into the presentation directly. Let me share my screen. So I hope everybody can see my screen. Is my screen visible?
no, it's not.
Just a moment. Let me reshare this. Share screen. Yes. Is it visible now?
Yes. Yeah.
Okay. So let's start directly into the. Again, thank you for the kind introduction. Let's start on this talk for today. I would be giving a brief about interferometric gravitational wave detectors, how they work, and what is LIGO India, what the project is all about, and why LIGO India, and a bit of current status. And since I come from a technology development center, the various technologies being developed as part of this activity, which benefits other domains of science and technology also. All of you would appreciate that fundamental science stands on the shoulders of the previous generation's technology to push science further and have a better understanding of both nature and the cosmos. Yeah, with that, let's start. So we had a good understanding of gravity for some time from Newton, which was essentially action at distance with the formula of m1 m2 by d square with a certain constant. And this kind of unified gravity on Earth and across the solar system, and was based on the works of Galileo, Copernicus, and Kepler. And this explained a lot of observational data and kind of put gravity on a very sound footing for quite some time. Subsequently, in the early part of 19th century, Einstein kind of reformatted or reformulated the gravity as a kind of a curvature of space-time and said that all things follow geodesy, and this led to a new paradigm of understanding of how gravity is manifest. And this I just kind of note here because the gravitational waves is an outcome of this general theory of relativity about viewing gravity as an aspect of space-time. And gravitational waves are one of the most intriguing predictions of the general theory of relativity. Essentially, it's a ripple in space-time or a vibration propagating in space-time fabric. And these are produced when you have very extreme astrophysical masses which are accelerating. So essentially, you have to have a time-varying quadrupole moment. So to have an analogy with electromagnetic waves, if you have a time-varying dipole moment, you have a propagating electromagnetic wave. Similarly, if you have a time-varying quadrupole moment of masses, the general theory of relativity predicts that there's a propagating gravitational wave. And since the coupling constants are very small, even Einstein believed that these are artifacts which will never be detected. And he felt that these are vanishingly small values. And that's what he wrote in his paper, that these are not going to be experimentally detected. However, when you have very large astrophysical sources like black hole binaries which merge, very close to the merger, they can produce sizable amount of gravitational waves. And so do neutron star mergers, which can produce sizable gravitational waves because of the quadrupole moment, and especially during the merger time when their orbital frequencies are in the frequency of few hertz to hundreds of hertz, and the velocity is close to speed of half the speed of light relativistically. So if you look at various possible gravitational wave sources, the main ones or the most strongest ones are coalescing binary systems like black hole or black hole neutron star or black hole neutron star mergers. But there are other sources also. For example, even kind of a burst of a supernova, if the core is expanding or core is collapsing asymmetrically, it can have a significant quadrupole moment, which can manifest as a burst of a gravitational wave. You can also have neutron stars if they have asymmetry, and so there's a quadrupole moment associated with that. If you have a small hill on a neutron star and if it is rotating, this can produce a continuous source of neutron star, unlike binary neutron star coalescence, which is more like a chirped burst or chirped signal from a gravitational wave, which has kind of a millisecond to a second kind of a presence. The neutron stars, spinning neutron stars, can produce continuous sources, so the detection can be a different technique based on frequency locking and other things, but these strengths are very, very low compared to the coalescence of black hole neutron stars. Last but not the least, that's the cosmic microwave background, the equivalent of the cosmic microwave background. It is a stochastic incoherent background produced by all the events in the cosmos, which manifests itself as the background gravitational wave in the cosmos. And this stochastic background is very, very weak. So we are very, very far from doing any measurements or having any sensors detecting this at any level. But these are the major four sources that can produce gravitational waves of measurable strength. And as I mentioned earlier, the most or the strongest ones towards which the interferometric gravitational detectors are focused on is the black hole or black hole neutron star mergers as coalescing binary systems. So this is a kind of a temporal picture about when these things were produced. So you have millisecond pulsars and supernovae, mergers in the milliseconds. Compact binary inspirals are in the hours. So these are the decihertz. So those are in the domain of space-based interferometry. And the supermassive black holes are done by pulsar timing arrays. Many of you will be aware that pulsars are very robust timekeepers. They have a very precise frequency of rotation. And if a gravitational wave passes through the intervening space of a pulsar, the timings of these are modulated because of the temporal modulation. And you can do data analysis to check for the fluctuations in the pulsar timings to detect gravitational waves. And the current pulsar timing array group has announced the detection of gravitational waves using this technique. And the stochastic background can be detected by looking at the CMB polarization. And that is something that is still to be worked out, though there have been some announcements which have then been withdrawn. So our focus for today's talk is in the 10 hertz to a few kilohertz kind of a source, which is the terrestrial interferometers domain, and where you can build terrestrial interferometers of the required sensitivity to do that. The reason why terrestrial interferometers cannot go below tens of hertz to detect other gravitational waves, even if their strengths are high, is because of what is called microseismic noise on the Earth. So there is a increased noise in the band of 2 hertz to 0.2 hertz, which is the averaging of all the earthquakes and tidal forces on the Earth, and which makes it quite noisy for ground-based detectors to detect in the region of hertz and lower. And that's why these decihertz and millihertz and nanohertz are space-based detector domains and not the gravitational waves. So terrestrial interferometers are well suited for 10 hertz or 20 hertz and above, up to a few kilohertz, and even megahertz. But then astrophysical sources mostly manifest in the region of 10 hertz to 100 hertz, and some neutron star, possibly rotating neutron stars in kilohertz, but hardly any sources that can produce megahertz at this point. But the problem with fundamental science, or the advantage of fundamental science, is that you are always surprised by experimental facts. So that is the. So that's the gravitational spectrum. Again, just to reiterate this part about ground-based interferometers, then space-based interferometers. So all gravitational waves detected till date are in the ground-based interferometers and the region of a few hertz to hundreds of hertz. And the pulsar timing arrays essentially are about supermassive black holes which merge, and these are in the nanohertz to millihertz kind of domain of measurement. So before we jump on to how the detectors work, I'd like to point you to a certain indirect detection of gravitational waves. Though the 2015 detection of gravitational waves by LIGO is considered as the first detection of gravitational waves in a human-made detector, the proof of existence of gravitational waves have been much earlier. So as I mentioned, there are pulsars which have a fixed timing scale, and you have a binary pulsar called the Hulse-Taylor pulsar, essentially named after the discoverers. And this is a pair of pulsars which are orbiting each other, and based on the amount of gravitational wave radiation emitted by these pair, their orbital decay is predicted to have a certain function by the general theory of relativity. And over an observation of something like 25-30 years, this has met the prediction of the general theory of relativity in terms of the decay rate of this orbit, or the decay rate of this binary pulsar orbits about each other. And this has been one of the first indications that gravitational waves do carry away momentum and energy. And this was one of the initial proof of indirect detection of gravitational waves, and this received the Nobel Prize in 1993 for indirect detection of gravitational waves for the discoverers Russell Hulse and Joseph Taylor as part of the work. Yeah. So, as I mentioned, even Einstein believed that the general theory of relativity is a mathematical artifact, or in fact, it's so small that whether it exists or doesn't exist, whether it's an artifact of the linearization. So it was not till 1950s and 1960s that the nonlinear differential equations of general theory of relativity were robustly solved, and people started to agree that general theory of relativity does predict gravitational waves. And there was the initial work by Joseph Weber, who thought that the best way at that point, given the technological advantages, was to detect gravitational waves by a resonant bar. The idea is very simple. So you take a cylinder of aluminium, and if a passing gravitational wave matches the resonant frequency of this aluminium, some part of the gravitational wave spectrum will get coupled to this mass, and this mass will get resonantly excited. And then you can use sensors on the cylinder, mostly PZT sensors, to look for this resonant vibration that has been set up in the cylinder by a passing gravitational wave. So this is what is called a bar detector. And Joseph Weber operated 2 of these separated by a few hundreds of kilometers for coincident detection. And though he did claim a few detections which had been disputed, and subsequent understanding and hindsight shows that given the strength of astrophysical sources that we currently know, these detectors are far from the sensitivities that are required to be able to detect gravitational waves of origins from binary neutron star or binary black hole mergers. So let's make a case for interferometer-based measurements. So with the advent of laser, and then the Michelson interferometer got a new upgrade using lasers. So let's just look out how we can do gravitational detection. So here you see a small GIF of a circular array of test masses. So if the gravitational wave is passing through the plane of your, out of these, emitted across the screen of your display, the passing gravitational wave will modulate the circular distribution of test masses in this manner. For one cycle, the vertical axis gets stretched out. Concomitantly, the horizontal axis gets compressed. And in the next cycle, the vertical axis gets compressed and the horizontal axis gets elongated. And here, essentially, the space is getting expanded and contracted. The particles are in the same place, but as we know, we measure distance using speed of light. So the measured distance from the center to the test masses changes. And that is the principle that we use in interferometry to measure gravitational waves using an interferometer. So if you superimpose the Michelson interferometer is a very simple device. You take a light source, in this case, a coherent laser source. You split this into two beams, one that is reflected to a vertical mirror and the other to a horizontal mirror. And then the light reflected from both these mirrors is then collected back, and the same beam splitter with splitted combines a portion of these beams onto the detector. And if the two arms L1 and L2 are exactly equal, you can do simple calculation to show that the phase shift of the beam splitter has an extra pi shift. So on the detector, you'll get a dark fringe when both the arms are exactly equal. And if these two arms get perturbed, as I showed the previous GIF, the two mirrors at the end of the arms can be treated as test masses if they're properly isolated and inertial in nature. The passing gravitational wave will modulate the distance between the beam splitter and the mirrors. In one cycle, the horizontal arm will elongate and the vertical arm will compress, and in the next cycle, vice versa. So this produces a differential shift of delta L, which is the strain due to passing gravitational wave. And this is manifest as the change in intensity on the detector because of the change in the phase of the interfering waves. So initially, if you set the detector a null detector where the two phases exactly cancel out, any difference in this phase due to the extra delta L will lead to an intensity on the photodiode, and that is what you measure and then try to find what is delta L, which is called the strain. So given the typical astrophysical sources for a binary neutron star in spiral at something like 20 megaparsec, the estimated strain is something like 10 power minus 21. So if you have two test masses on Earth separated by a distance of a meter, binary neutron star merging at a distance of 20 megaparsec will produce a change of 10 power minus 21 meter for this two test masses separated by a meter. So that's a small change, an extremely small number to detect. And that's what makes the LIGO detectors engineering marvel in being able to push beyond the limits of what physics allows and to be able to detect this level of small change because of passing gravitational wave. So let me kind of make a case for how the LIGO detectors work, and if you want to detect that. So if you want to do more than just the binary neutron stars, and if you want to go beyond and look at black holes which are very far away, the target sensitivity for an advanced LIGO detector is something like 10 power minus 24. That's the strain sensitivity you want. So that's the sensitivity of the detector. And because if the test masses are a kilometer separated, then it's 10 power minus 24. If they are separated by 10 meters, then it becomes 10 power minus 23. If they're separated by 100 meters, it becomes 10 power minus 22. So you get a scale factor because of the L, because the longer the arm length, the more the accrued strain multiplied by the length. And that is one of the reasons why these interferometers are such kilometer lengths. So LIGO detectors, both the US and the Indian version they were building, the arm length, which is the distance between the beam splitter to the mirrors, is of 4 kilometers in length. And that directly gives you an advantage of a factor of 10 power 3, so 10 power 4 or something like that. So that gets you delta L in the regime of 10 power minus 20 meters that you need to measure in terms of displacement. So when you have a typical laboratory interferometer that you use in a lab for measuring displacement, a Michelson-based interferometer, these can typically achieve 10 power minus 9 or nanometer kind of resolution. And from nanometer, you have to thread by another factor of 10 power 12 to go to 10 power minus 20 kind of a displacement measurement. So we'll see how the optical configuration of LIGO enables you to do that. So when I was mentioning about using the interferometer as a detector for gravitational waves, I mentioned that the two arms are exactly set such that they produce dark fringe at the detector. So if the output port is a dark port, then if you do a little bit of calculations about at the beam splitter, you'll see that all the light goes back to the laser side or the bright port. So the beam splitter is splitting the two beams, they combine back and then again produce two ports, one towards the detector. And since at the detector, the phase shift is exactly λ/2, that's how the mirrors are adjusted to get completely dark fringe on the photodiode. This would require that all the light is then reflected back in the laser side. And this power can be again put back into the interferometer, sorry, using another mirror, which is acting coherently with the rest of the interferometer. And this is called a power recycling mirror. So typically the laser power used in a laboratory is a milliwatt. So the short noise limit is something close to the nanometer or picometer kind of measurement. But in the LIGO, the power is already something like 200 watt. So because of that, the short noise limit for that interferometer has a factor of watt to a milliwatt, 200 watt to a milliwatt, a factor of 5. So we already get an advantage there. And apart from this, using this mirror, which is called the power recycling mirror, I can put back this power back into the interferometer, and that will be dictated by the reflectivity of this power recycling mirror. And if the power recycling mirror and the rest of the interferometer becomes a complex Fabry-Perot cavity, if I set the finesse of this Fabry-Perot cavity to a factor of 10^2, I get another power enhancement inside the interferometer, factor of 10^2 approximately. So that's almost 10^7 factor that we have got around already because of the 200 watt power and the power recycling phase. So the next step is if we can enhance the length of the interferometer. The one way to enhance the length of the interferometer is to bounce the mirror, the light in the arms multiple times. So this could be like individual mirrors, which is folded back and forth in a cascade. But the equivalent of that is what is called a Fabry-Perot interferometer. They do it coherently instead of doing it in a zigzag fashion. You can do it in line. So you can introduce two mirrors in each arm, which is called the Fabry-Perot input mirror. And each arm works like a Fabry-Perot interferometer itself. So if you set this finesse of this cavity by choosing the right reflectivity of the Fabry-Perot mirror, and if they are resonant, then the light inside the Fabry-Perot mirror travels it travels a distance which is the length of the cavity into the finesse. So effectively the arm gets multiplied by the finesse of the length. So if the physical arm length is 4 km, and you set a finesse of something like 100 or 200, then the arm length effectively becomes for the interferometer 100 into 4 kilometers, something like 400 kilometers. So that's the another factor enhancement of 10^2 to 10^3. So we are already in the domain of 10^11 kind of an advantage here. The next is the signal recycling mirror. So the general relativity predicts that the speed of light or the speed of gravitational waves is also the speed of light. And all of you from fundamental electromagnetics will realize that if you want to have detection of electromagnetic waves, you can choose a wavelength or an antenna which has a λ/4 kind of a light, a λ/4 kind of a length, which is resonant for that. Similarly, if you look at the interferometer arm length, they are something like 400 kilometers, but the wavelength of the gravitational waves, if they are in the region of 100 hertz to 1 kilohertz or even 10 kilohertz, the effective wave or the wavelength of the gravitational waves will be hundreds of thousands of kilometers. So the arms are very, very small compared to the wavelength of the gravitational waves. So in some sense, the interferometer is always working in one quadrature of the gravitational wave itself. So you can essentially take the output of the interferometer and put it back into the interferometer so that it accrues more phase in the next cycle and the next cycle and the next cycle. And this is called signal recycling. Effectively, you can imagine this as if instead of putting the signal recycling mirror at the output port, you can have a cascade of interferometers which are kept in a series so that the output from one interferometer you're introducing into the other interferometer, which is accruing more phase because of this moving gravitational wave. Then again in the other phase. So essentially, you're building a cascade of interferometers in a virtual fashion by putting the signal recycling mirror. The signal recycling mirror keeps putting back the signal into the interferometer, and by choosing the right finesse for this, for example, in LIGO, it's a factor of 100. So by choosing a factor of 100, the signal spends 100 times in the detector, accruing the same quadrature and improving the phase modulation on the differential arm phase from the gravitational wave interaction in the interferometer, and that is how you push another factor of 100. So all these factors of 7 because of power recycling of 100, then the Fabry-Perot arm of another 300, and these bring you to the limit where you can start to detect sensitivity displacement noises displacement limits of 10 power minus 22 to 10 power minus 23. And that's precisely how the advanced LIGO detectors are able to detect such small differential motion between the two arms, which are of 4 kilometer length. So mind you, these are not absolute measurements. This is the differential change between the two arms. So I have a small movie here to show how the interferometer effectively works. So the beam is split into two parts. So what the beams essentially are doing are displacement measurements, because they're measuring the time taken for the beam to travel from the beam splitter to the mirror and return back at the beam splitter, which is then imprinted on the face between the two mirrors, or the two beams that are merging there. And the interferometer is set in the dark port. So initially they are set such that they directly interfere with the output port. And a passing gravitational wave, when it kind of modulates this, then changes the phase relationship between the two beams, producing the output, which is then used to measure the gravitational wave parameters and then go and predict what kind of a source emitted these gravitational waves. So with that basis, let's just move on to the LIGO detectors. So LIGO stands for Laser Interferometric Gravitational Wave Observatory. So this was a project that was funded by NSF. It was a project that was proposed by LIGO labs at Caltech and MIT with collaborations from across the world, including Indian people who did most of the data analysis for these detectors before we got involved in the experimental and the detector building effort. So these two detectors were built in Hanford and Livingston, and they built across continental US, and they're intentionally built across continental US. I'll come to that later. And they're currently operating, and they are been operational since 2015 and have produced many amazing results along with Virgo, which is the European detector. So if you please keep in mind that the distance between these two detectors is approximately 3,000 kilometers, which is the time of flight. If you take the speed of light as the metric, then the time delay between them is around 10 milliseconds. This is an important parameter for source localization. I'll detail that a bit later. So this is a aerial view of the two detectors. So what you see at the corners, at the apex of the two arms are the buildings which house the corner station, which is the beam splitter and the associated laser and other paraphernalia. And the two arms that you see are the concrete covers of the vacuum tubes. We'll see a little more detail later. And at the end of these two arms, you have the station which handles the end mirrors, which are reflecting the light back from the corner station towards the beam splitter. So one is in Livingston and the other is in Hanford. And as I mentioned, these are funded by the National Science Foundation, and they've been operating from the later part of 2015. And currently, something like 5 runs of science runs have been completed, the Advanced LIGO configuration. So the Hanford Livingston detectors are separated by 10 millisecond. And if you look at India, it's on the other side of the globe. So if you plot the distance from Hanford to the location where LIGO India is being built, it's around 36 millisecond, and Livingston to that location around 39 millisecond. So other than Australia, probably we are the most competitive in terms of the largest triangle that can be built on Earth of gravitational detectors. And that is important because these the area encompassed by the triangle is a metric of the error of the source localization of the sky. When you use the delay from the 3 detectors to compute what is the normal vector to this triangle, which points to the detector on the sky. And this allows to do source localization. And that's a very important parameter to do what is called multi-messenger astronomy. If you want to follow up with other telescopes like optical, radio, and other things, you will hear a little more details subsequently. So this is one of the reasons why LIGO India is being built, because it provides better sky localization. So currently you have LIGO Hanford, LIGO Livingston. Geo 600 is a 600 arm length detector, which is a high frequency detector, which is being decommissioned in December. So this is not a really competitive detector for the 10 hertz to 100 hertz kind of a line width. Virgo is a 3 kilometer detector, but it operates almost like at 30%, 20% sensitivity of LIGO Hanford and LIGO Livingston. So this has been part of the science runs and currently is being upgraded. We have Kagra, which is in the Kamikonde mines, and this is a Japanese detector. And this is operating at something like 1/10 the LIGO detectors currently, and are currently being upgraded to match detectors. So LIGO India and LIGO Hanford and LIGO Livingston are all based on similar technologies. So we hope that the lessons learned at LIGO Hanford, LIGO Livingston allows us to build detector with a similar sensitivity and operate with similar sensitivity. So that all three detectors will have the same SNR, which allows you to do source localization with a very high accuracy. So a bit of history. The first gravitational wave detection happened in the September of 2015. And so the nomenclature goes as GW15, which is the year of detection, 09 is the month, 14 is the date. So this was detected on September 14, 2051. And this is the first gravitational wave detection in a human-built detector. And you'll see the two detectors have similar waveforms, and the delay from that is used to calculate the distance. And the residuals are purely noise within hardly any artifacts in them. And that is the justification why two detectors were required, at least to make sure that these are really gravitational waves, and also then to do the follow-up of pointing on the sky also. So this is the computed in spiral, calculated from numerical relativity, and then matching the template for that. So these templates match very well with the predictions from general relativity, both for the in spiral, the merger, and the ring down, which sheds the remaining momentum of the merged black hole. The other most significant detection immediately after that was in 2017, 0817, which is in August. So this was a merger of neutron star. And neutron star mergers are interesting because then you get to see a lot of electromagnetic follow-ups. And this was detected by LIGO detectors and Virgo also. And this neutron star merger was then, followed up by other telescopes. So the trigger from the gravitational waves was sent out to all the other telescopes like visible and infrared telescopes, large telescopes, radio telescopes, neutrino detectors, and gamma ray detectors. And all of them were able to look at signatures of the electromagnetic and particle radiations from these merger of a kilonova formed by this neutron star merger. And probably was the start of a new era of what is called multi-messenger astronomy. And this is an important tool in understanding the universe in multi-bands and multi-event detection, both gravitational waves, visible radiations, radio waves, neutrinos, and gamma rays from the same event. So to date, something like 200 events have been detected. Unfortunately, the ones that have been studied and declared, hundreds of them, are still black hole mergers. There have been not many neutron star candidates, though there are some in the offing which are being analyzed. Neutron star mergers are interesting because they get observed in other wavelengths also, domains also, visible, radio waves, and particle astronomy. But black hole mergers have also thrown up many surprises. There is a large collection of tens of solar mass black holes, intermediate range black holes, which were not predicted by the standard formation of star formation. And these are being puzzled over as to how they came into occurrence as cascaded merger of black hole binaries or any other mechanism. So this is a current detection map of the LIGO Virgo detectors that have been running for the last 10 years. So one of the follow-up outcomes of the neutron star merger solved a few puzzles about origin of various elements. For example, the abundance of gold and platinum had always been a puzzle as to how standard nucleosynthesis can account for them. So the measurements done with the first neutron star merger with other optical follow-up and other measurements show that these are formed during neutron star merger. A large portion of gold and platinum is made by that. And most of the radioactive elements like thorium, uranium, and plutonium are produced primarily in merger of neutron stars. So this was one of the physics outcomes in a very different domain of nuclear and atomic physics. So this is the case for LIGO India. So if you take LIGO and Virgo, which are the operating detectors of the required sensitivity, these are the error ellipses. When I mean by error ellipses, so if you look at different portions of the sky, and if these detectors are operating with the similar sensitivities, then this is the window over which you have to hunt with an optical telescope to locate a source. So smaller the error ellipse, the faster you can identify a kilonova if a detection happens in this portion of the sky. So in the first part of the map, you'll see the error ellipses are pretty large in certain portions. These are governed by the antenna pattern for the detectors on the Earth and the orientations they have. and also the locations also. So Virgo and the LIGO detectors form a smaller triangle. And the moment you introduce LIGO India, you will not only see that the error ellipses become small, some of the blind spots that you see in the left side disappear completely, and you have full sky coverage, allowing you to observe gravitational waves from any portion of the sky and localize them in the sky, not missing out any of the events. So that was a model. This is for real detections that have happened. So till date, all the detections that have happened, if you try to map the error ellipses, the purple one show the LIGO Virgo events, the localization given by the two LIGO detectors and the Virgo. And if LIGO India had been operating during this era, then the error ellipses collapse to the blue ones. And that is the main gain that you get by having LIGO India, allowing you to do multi-messenger astronomy with higher accuracy and also with larger signal to noise ratio, to being able to do larger source collection and cosmology with that. So a bit of history. So though we are starting to build LIGO India, this has been something that's been pursued for almost three or more decades. So in 1990, Ayuka and Arakat had been trying to build a 100-meter prototype, which never got funded because it was deemed to be too ambitious. So in 1995, the ASIGA collaboration, which is essentially the Australian team which works on gravitational waves, the effort was to build a kilometer-class detector at Perth. This also did not fructify because the ASIGA group did not get the funding from Australia. We were supposed to participate in 20% level of in-kind contribution. So 2009, the Indian consortium, which was called INDIGO at the time, had proposed to the Mega Science sub-panel of the Planning Commission to support LIGO India. And that is where the whole story starts. And what you currently have as LIGO India is, this is the starting point for that. And this is a collaborative effort with the LIGO laboratory, where they are sharing one set of detectors to build a LIGO detector India, which is identical to the other two LIGO detectors. And these components are built as part of a H2 detector, which the idea was the Hanford detector will have two detectors, one at 2 kilometer arm length and 4 kilometer arm length, to learn the technology for cavity locking for 2 kilometer before going to the 4 kilometer. But then it was after the initial LIGO that was deemed unnecessary because people learned the technology of locking 4 kilometer long arm lengths. And these components which became available or free were part of the contributions that we received for LIGO India to build a third detector in India. So the lead institutes for this project is IUCAD, DCCM, IPR, and Arakat. And the collaboration is with the LIGO lab, which is spread out between LIGO in Caltech and LIGO in MIT, and which are funded by NSF. The LIGO India project is funded half-half between Department of Atomic Energy and Department of Science and Technology. So after the proposal to the Mega Sciences Committee, we were tasked to find a site. And after the site was located, we signed an MOU with NSF, which is the funding agency for LIGO US. And this was signed in March of 2016, which initiated the procurement of the site and the preparation for the project itself. So this is what we hope to complete by end of this decade, April of 2030, which is the LIGO on the observatory at Aunda. Detail this a little bit for. So this is located in the Deccan Plateau. As I mentioned, the site survey started out with something like 22 sites across India in the early 2012 to 14 era. And this consisted of 2 sites in Rajasthan, 3 in Madhya Pradesh, 2 in Karnataka, 3 in Andhra Pradesh, and 2 in Maharashtra, out of which 4 were shortlisted, 1 in Rajasthan, 2 in Madhya Pradesh, and 1 in Maharashtra. And the Aunda site had the highest metric in terms of the microseismic noise. So the microseismic noise is the average noise, as I mentioned, from all the tidal beating, all the weather phenomena on the Earth, typhoons and storms and everything. So the Earth crust shakes at a frequency of something like 2 to 2.2 hertz with a displacement of a few nanometers. And that's the limiting vibration on the Earth, which limits down-based detectors to not go below 10 hertz. And so the site was chosen based on the minimum value of this microseismic noise. And you would be happy to note that the LIGO on the site has half the noise of the Hanford site, which is better of the 2 sites in the US. LIGO Livingston is a little more noisier than Hanford. Hanford is more silent, but we have a noise spectrum which is half the LIGO Hanford site. So hopefully, if we take advantage of that, we can operate at a sensitivity which is almost twice that of what Hanford has been able to achieve. So the site acquisition has been done. This was part of the pre-project before the main sanction happened. And the site looks something like this. The corner station, we have a square patch of, excuse me, 650 meters by 650 meters. And at the end stations, we have a rectangular patch of 250 by 400 meters, connected by a land strip of 150 meters width and 4 kilometers length. So this site is completely in the position of DAE, and construction is in progress. I'll detail that a bit. So after acquiring the site, we had a 14-month basic seismic survey to have the baseline data across the variation across the whole year, and also to have a baseline across which we can compare our detector behavior in terms of the seismic noise that we see in the detector because of other building and HVAC noises and other things. So this was the baseline that was completed. And this allows us to design the facility with the required isolation to match and make use of this low noise field. So at the site, we currently have our site office. We have a dedication pillar, which was inaugurated by the Prime Minister on May 11th. We had the financial sanction for the project on April 6, 2023, with a duration of 7 years, with the project completion in April of 2030, with a total project cost of 2,600 crores, shared half-half between the Department of Atomic Energy and the Department of Science and Technology. And this project is currently on schedule, and we hope to complete this detector by April of 2030. So let's get a little deeper into how an advanced LIGO detector looks like. I mentioned about the various techniques that are used to improve the sensitivity. So let me walk you through the layout of the optical system for the advanced LIGO detector. So you have at the left end the laser system, and I'll come back to the laser system in a little more detail. This laser system is then this laser system produces a very narrow line width laser, because you would appreciate that the whole interferometer has to operate as a single coherent element. And the 4 kilometer arm length is not just the coherent length. You're using a fabrication arm to multiply it with a factor of 100. So that becomes something like 400 kilometers. And then the power recycling and the signal recycling are folding it back multiple times. So you need a coherence length that is a few 100,000 kilometers. So if you translate that back to lambda, so this works out to a few hertz at 1 micron. So 1 micron laser, if you calculate the frequency, it is something like 1000 terahertz. So in 1000 terahertz, the laser has to have a frequency jitter of not more than 10 hertz or less. So that's the kind of laser system that is required to match the required coherence, so that you can operate this in a coherent fashion, do power recycling and signal recycling along with the fabrication arms also. So apart from that, you also need to have very low noise, because as you saw, the final output is an intensity modulation of the photodiode. So the laser amplitude noise can kind of reduce the signal to noise ratio. So the laser output, though it is designed to have very low noise, it's not sufficient. So you use what is called the input mode cleaner. So the input mode cleaner is nothing but a resonant cavity, where you make it resonant for the laser mode and also the frequency of the laser. It accumulates laser power. It's a resonant cavity, so it accumulates power. And in the steady state, amount of power that you put in is the power that leaks out of the cavity also, apart from the scattered and the absorption losses. Sorry. So it acts like a optical capacitor in some sense, as an analogy. It's a very loose analogy. Please don't use it very extensively. So the intensity of the laser system is, or the laser output is kind of suppressed by a factor of the finesse, which is the light finesse with or the quality factor of the cavity in some sense. The quality factor is nothing but the intracavity power to the power loss per cycle. So that is a measure of the quality of the optical quality of the cavity. So this input mode cleaner improves the laser beam in 3 sense. It decreases the intensity noise by a factor of the quality factor. It improves the pointing. Pointing is the jitter in the direction of the laser beam. You're trying to point a laser beam that is traveling 4 kilometers. So any small angular motion will produce a very large displacement. So you cannot align the interferometer. So that is improved by this input mode cleaner. And it also improves the frequency sensitivity, because this cavity is resonant for a certain frequency. So any frequency jitter is rejected by this cavity and does not lead to buildup. So the cavity output is a very pure wavelength. So the laser parameters of the intensity, frequency, and pointing are improved by a factor of the Q factor of this cavity, matching it to the requirement for the interferometer. So ignore the PRM for the time being, just look at the beam splitter. The light from the laser after the cleaner is split by this beam splitter and then makes it into the two arms, which are FabriPro arms. As I mentioned, these input mirrors are called input test masses and the end ones are called end test masses. And this input test masses and the end test masses form the FabriPro cavity. And these multiply the path length multiple times. The light bounces between them by a factor of 100 or more, and multiplying the 4-kilometer arm length by the same factor, and then return to the beam splitter. This happens for both these arms. So both the arms have an effective arm length, which is 400 kilometers, and that again merges back at the beam splitter. And the two arms are adjusted such that the beam splitter again produces the dark port towards the detector, so that you have very little light on the detector, so that you can use very high gain for the photodiode, and you don't saturate the detector with intensity. And the advantage you have is that the bright port, which is towards the laser, most of the power is reflected back to the laser system. And that is where the role of the PRM comes in. So you put a suitably chosen mirror at the PRM, which reflects back this intensity back into the cavity, building up the cavity power by a factor of 100, which gives you better shot noise. The shot noise is because of the discretization of the light field, which is the quanta. So if you have 1 milliwatt, the shot noise is the granularity of the photons in that 1 milliwatt. The moment you make it 10 milliwatt, the shot noise goes down by root of power. So then you have more photons. So you can go to lower phase sensitivity, similarly at 100 watt, so on and so forth. So as you increase power, the shot noise comes down. And that is what you achieve by this PRM, which is power recycling. And the secondary recycling mirror is essentially, as I mentioned, you are using this interferometer multiple times. So a passing gravitational wave modulates the two arms of the laser, accrues in a phase of, let us say, a few nanoradian, and that is again put back, accrues another factor of 10 power minus 9 nanoradian, 2 nanoradian, for example, 3 nanoradian, 4 nanoradian. So you have a multiplication factor because of the SRM, and the choice of the SRM dictates how many times it passes through before it is put out to the output port. At the output, you have the output mode cleaner, and this essentially does what is called mode filtering again. When we had this laser, we had a very pure TEM00 mode of the laser, which was filtered by the input mode cavity. And the whole gravitational wave is imprinting its signature on the TEM00 mode. But you would appreciate that the TM00 mode is disturbed to some extent by the real apertures of the real surface of the optical system. The optical systems are not idealized systems. These mirrors are polished to exquisitely small flatnesses of lambda by 1000. Lambda by 1000 is Armstrong level. For example, lambda here is 1 micron. So 1 micron to 1000 gets you to something like a nanometer and 0.1 nanometer and less in Armstrong level. That's the level of flatness all these optics have. But in spite of that, because there's multiple reflections that happen at the FabriPro and the multiple reflections because of the PRM and SRM, even the small deviations of lambda by 3000 start moving power from the TEM00 mode to the higher order modes. And these higher order modes can then reduce the signal to noise ratio on the photodiode. So at the output mode cleaner, what you do is you build a cavity which is resonant for only the TM00 mode, which selects the TM00 mode only, makes it resonant, and rejects all the other higher order modes as the output filter. And that TM00 mode is fed to the photodiode as the gravitational wave readout, and improving the signal to noise ratio by rejecting the higher order modes because of the aberrations, the optical components. So in some sense, this is a very simplistic layout of the optical system, because you'll appreciate that all these components have to be maintained in relative alignment in spite of the motion of the Earth and also the density fluctuations in air. Obviously, this interferometer is not going to operate in air. It has to be in vacuum. And then you have to make sure that all these components are in inertial space, in the sense that all vibrations on the Earth, motions of the Earth are not coupled to any of these elements. And that's the engineering crux of the whole interferometer, to make sure that the interferometer works as desired in spite of sitting on Earth and being immersed in the atmosphere. So the laser itself sits on a pretty large table, which starts as an oscillator and then a preamplifier and an amplifier. I'll give a little more detail as I go forward. The core optics are something like 340 mm diameter fusilica masses of 40 kg, suspended by fusilica fibers again as an isolation. These are pendulum isolations. And these final core optics have a 7-stage isolation from the ground, 4 of them active, 3 of them passive. I'll give more details. And all the intermediate optics are chosen with the right amount of isolation, 3 stage, 2 stage, 1 stage, depending upon the optical lever that they have and the amount of noise they will corrupt the interferometer about. And so each of these elements is isolated from ground and sits inside a vacuum system to make sure that the density fluctuation of air does not introduce any differential signal in the interferometer. So unlike standard optical tables where you put optics on a post, here all the optics are isolated by suspending them from suspensions and making sure that they are isolated sufficiently from the ground vibration, which are few nanometers per root hertz in the band of interest for LIGO. So this is kind of a schematic layout. So vacuum systems are built around each of these optical tables on which the components sit, and the intermediate ones are connector-based spools. So the pink ones that you see are called horizontal axis module vacuum systems. And to keep cost low, the chambers have been built such that they are self-similar. The tables are different. Each of them have different optical layout, but the chambers are identical in every sense. So they are multi-purposed and they are manufactured multiple numbers. So the purple ones that you see are the horizontal tables where the components are small and they're mounted on optical tables inside the vacuum system. The orange ones are the ones that are for the core optics, where you have to hang the whole optics from the top, and they're called the beam splitter chamber or the basic sciences chamber. They're called the BSc chambers. So each LIGO detector uses something like 5 BSc chamber, one to house the beam splitter, one to house the input test mass and the end test mass in one arm length, 2 of them, and the other 2 in the other arm, making a 5 of them. And the ham chambers are for the input filter cavity and the output mode cleaner and other thing. So you see an extra set of filter cavity and other things. I'll come to that later. That's a squeezing part to go below the shot noise. So after the O3 run, LIGO US have introduced squeezing, which essentially allows the interferometer to operate below the standard quantum limit, achieving required sensitivity with the lower laser power. So one way to fight shot noise is to increase the laser power, but that comes with the penalties of instabilities in the laser because of higher power on the optical mirrors, which can change curvatures because of thermal loading, and also optical lever effects if they are unsymmetric. So these instabilities limit the amount of power that you can put in the interferometer, limiting the sensitivity. So beyond that, when you want to push the sensitivities, then you use a squeeze light source to go below the shot noise, given the laser power to do that. So currently, LIGO India is being built without the squeezer, but the civil and the vacuum facility have provisions for the squeezer, and we are developing a squeeze light source at Aracat. And so we hope to arrive in the squeezed light configuration, similar to the current configuration of LIGO, which is called A+ configuration. So this is the kind of a schematic that shows the chain of suspensions that allows the core masses to be isolated. So let's start out with the left-hand part, which is the support pier, which sits on ground. That has a pneumatic isolator, which is called the HEPI, which is called the hydraulic external pre-isolator. So this essentially is a very low frequency compensating system, which compensates small ground motion skills and compensations, which then couples through this into the vacuum system. And inside the vacuum system, you have seismometers and geophones, which measure tip and tilt of these platforms. And then they feed forward and correct the intermediate stage and then the final stage. So this HEPI and the 2 ISI stages form 3 levels of active isolation systems, which are constantly measuring and correcting for the ground motion. And from that platform, is suspended a 4-stage, what is called a passive isolation system. So to understand the passive isolation system, the simplest way is to hang a pendulum. If you hold the pendulum in your hand and move your hand very slowly, you'll see that the mass follows your hand. But if you move it at the resonance frequency, it gets coupled. Even small motion produces large motion. But above the resonant frequency, if you shake your hand very fast, the pendulum remains stationary. And that's the principle that's used here. So the pendulums are designed with the frequencies which are in the region of something like a few hertz, the resonance of a few hertz. So far away from the resonance frequency, you have a 1/f kind of an isolation. So each pendulum stage provides a 1/f isolation. So 4 of them provide 1/f, 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 1/f. So 1/f or 4 kind of an isolation. And that's what is the 4-stage quad suspension, which gets you the quad optics or the final core optics to achieve the required suspension. But you'll see 2 sets of suspensions. One is the test mass, and at the back of it, what you call is a reaction chain mass. So you'll appreciate that you'll have to align this test mass to align the interferometer. But to align this interferometer, you have to actuate it. But if this actuator is going to sit on ground, then the relative motion between the ground and the actuator is going to introduce a ground noise into the mirror itself. So your relative reaction mass with which you're going to actuate your test mass also needs to go under this isolation. And that's why you see the two equivalent chains of suspensions. One is the reaction mass and the other is the actual optical element, which is aligned with respect to the reaction mass. And the actuators, in this case, the electrostatic actuators, which are kind of gold fingers printed on the two mirrors, and you use high voltage to actuate them by electrostatic actuation. That's how the core mirrors are actuated and aligned in the LIGO interferometers. So this is the engineering build for it. So the intermediate masses are mechanical masses, whereas the final stages, the final stages are built out of fused silica. The penultimate mass and the final mass are suspended with fused silica wires from the same material as the build of the glass, so that the mechanical resonance or mechanical Q of this assembly is of the order of 10⁻⁷ to 10⁻⁸, so that the thermal noise or the mechanical mode noise is very far away from the sensitivity of the detector that we want, so that you don't have any excitations due to resonance, and you get the required isolation of 1/2². And these require proper design of the suspension fibers, the welding of the tabs. So there's an extensive amount of FEM and design engineering to achieve the required amount of isolation without introducing noise in the whole suspension. So that was all about vibration isolation, but you'll appreciate that air is highly phase sensitive medium, in the sense that if the temperature of air changes, the refractive index changes by some amount, and a meter of air can reduce phase shifts of the order of something like few tens of lambda for every degree, and that is a few tens of orders higher than what the sensitivity we want for the detector. So obviously you cannot operate in air. So the whole of the interferometer needs to be immersed inside vacuum and operate under vacuum. And if you calculate the polarizability of light scattered by the residual air to be below the detector sensitivity for LIGO, you would calculate and find out that the vacuum has to be of the order of 10⁻⁹ millibar, which is ultra high vacuum. So the whole interferometer detector, the optical components sit inside a vacuum assembly, and that whole vacuum assembly needs to be pumped down to a pressure of 10⁻⁹ millibar, which is ultra high vacuum, and that itself is a technology that is required to be mastered for this large scale volumes. You would have seen vacuum chambers in various labs, which are a few meter cubes and nothing. Here it is the effective volume of the whole vacuum system is like 1000 meter cube, and that's a very large volume to pump out and achieve ultra high vacuum. So the vacuum chambers achieve the required environment for the interferometer, but then you have to house them to make sure that the vacuum system is also protected. So that's where the civil infrastructure comes. But you have to build a civil infrastructure which does not increase the noise of your ambience and put up the detector, because when you build a building, you'll have the AC system for it, you'll have various equipments and mechanical systems working in it. So the total noise coupled to the interferometer should not destroy the sensitivity. So there is a serious amount of engineering that goes into the building of this detector. So currently, the preliminary design for the vacuum system prototyping has been completed. The design for the engineering buildings and the design validation for the engineering has been completed. And the contract for building the civil and the vacuum infrastructure has been given to L&T, which is Larsen & Toubro, a large engineering firm in India, on March 13th. And the site has been handed over. So currently L&T is starting to do the site leveling and starting the construction. And they hope to complete everything by September of 2029. And we hope to be up and running by the end of this decade. So while the building is being completed, we need to scale up our expertise and also build and test some of the components, detector components, assemble them and test them as we receive as contributions from the US. So as part of that, we have set up a facility at Aracal called the LIGO India Testing and Training Facility. So in some sense, this is one section of the corner station. It is around 25 meters by 75 meters of isolated slab floor. So in the corner station, as I mentioned, the building vibration should not couple. So the floor is isolated from the building, and a similar kind of a building is built at Arakat to do the preparatory work, and with the required same specifications and vibration isolation and the cleanliness to operate the detector, which we use to learn all the techniques. So this was inaugurated on December 2nd, 2024 by Secretary DAE, and it's up and running now. So we have a small 10-meter interferometer as a test interferometer for the controls people to learn how to align a suspended interferometer. Most of our optics in the classical domain had been done on tabletops. And so this would be a new experience for the control group to align detectors where the optics is hanging from fibers, and you need to kind of operate them by suppressing pendulum motions and vibrations and still maintain alignment of the detector. So this is an expertise building facility. And this facility will also use for assembling and partially testing the detector components while the site is being built. So almost 1/3 of the detector components will be tested here before they arrive at the site for further integration and building the 4-kilometer arm interferometer. So this is another shot of the 10-meter. Currently, we are upgrading this interferometer with fabrication arms. Currently, it's a simple Michelson. So the controls people have a less of a hardest task to control them. Currently, we are upgrading and adding the fabrication mirrors. So that is something which will add a bit of complexity.
Gopi? Sir, is the presentation stopped?
Roshni online?
Yes, I'm there. Let me check with Sendhil, sir.
Okay.
Gopi, I'm not able to understand what has happened. Sir has also, I think, got kicked out of Zoom.
Oh, yeah, I think sir is not there actually.
Let's wait for a couple of minutes and
Might
see.
might be he's turned back, I think.
Yeah, he
Maybe
might come back. Yeah.
Can you reach out for him by
Yeah,
mobile?
I tried ringing. He's not picking the call. So
Is it?
might have happened. Yeah. Maybe his connectivity issue or something. Let's see.
Yeah, I think so. Yeah.
Yes, sir is rejoining. Uh, Gopi, sir is trying to rejoin. Can you check that? So your microphone is not connected. It says that you're joining.
Hello, can you hear me now?
Yes, yeah, we can.
Yeah, sorry, my connection dropped off. So can you point me where I dropped?
So is your slides,
Yeah,
your
I'll just share my
presentation?
slides. Yeah,
Yeah.
I'll just share my slides. Yeah, so I think I was talking about the 10 meter.
Just before, yeah.
Yeah.
Mm.
So I think I'm coming close to my time. I think I'll try to run through slides and then take some question answers also.
Sure,
So
sure.
10 meter kind of spans various technologies that we have learned. And as I was mentioning, we're building the squeezer also because this is something that we had to build on our own for LIGO India. It's not part of the contribution from the LIGO US. And this is a configuration that we'll be building in the time scale of 2028 to 2030. And the intent is to arrive as an A+ configuration so that we have all 3 LIGO detectors having similar sensitivities to achieve the best possible SNR to do that. Yes, let me skip here. So we are also developing facilities to build the optics, which has various kinds of technologies to achieve the required micro roughness and flatness. So this is a project that has been funded by DAE to do the backend technology development. So this is in progress. We have set up the metrology facilities. We have got the new optics fabrication facility in place, and we are starting to populate all the machines. So this facility will allow us to build the core optics within the country if required, and also contribute to future gravitational wave detectors as we move forward. One of the key limiting factors are the Brownian noise of the coating. As I mentioned, the sensitivity of these detectors are so high that the classical idea of things don't work. Even the minimal Brownian noise on any material starts interfering with the detector sensitivity. And you hardly ever worry about Brownian noise in your optical system, but the quantum noise and coatings can do that in the main band of LIGO detectors. So there is a large search for the best possible optical coatings, and this is something which is based on the thermal dissolution theorem. You can choose materials which have very low refractive index variation or dn by dt and match them with the thermal noise. And to qualify them, so there is a lot of groups in India also working on thermal noise, developing coatings with low thermal noise. But our effort is to set up a low thermal noise interferometer to qualify these optics, and this is something that we're currently working on. I'll move on forward. We also set up the facility for this fiber drawing, which is a key technology for suspending the optics. to achieve the required isolation. So that is in progress, and this we are doing it with the Glasgow University. As I mentioned, LIGO in the US was built as international collaboration, and this quad suspension was a contribution from Glasgow University as part of UK's contribution to LIGO detectors, and this is a technology that we are doing under collaboration with the Glasgow University at UK, and this is funded by an STFC-DAE funded project, and you see some of the colleagues from the LIGO-India Project working at University of Glasgow in Professor Giles Hammond's lab, learning how to draw fibers and do end-tab welding. Pre-stabilized laser, I'll just keep a bit. This is the laser that we're currently starting to assemble. Components are starting to arrive, and this will be built in the testing and training facility currently. This is a clean room for that before we move this laser to the site. All the vacuum systems have been prototyped. Here you see the actual prototypes of a ham and a VSC chamber. They are currently undergoing pumping to validate, and so all the technology for vacuum system is now available within the country. One of the cryo pumps has also been prototyped, and there's a test bench to do the beam tube for the 20-meter also. So in a sense, the vacuum system that has to be built in the country, all the unknowns have been sorted out. LIGO and L&T has all the required information to go ahead and manufacture the vacuum system for LIGO. So in the closing, I'd like to mention that though LIGO detectors achieve an exquisitely high sensitivity of 10⁻23 for displacement noise, we still believe that these are nascent times in terms of gravitational detection, and you can match them, or you can kind of map them to the small telescopes that Galileo used to do groundbreaking detections. But we hope that the way the optical telescopes grew to a few meters in diameter, and you have currently that 30-meter telescope being built, the sensitivities of gravitational wave detectors will also grow in similar scale in the next decade or two, and do more science discoveries. Again, these are flashback to the gravitational wave spectrum. So we have just touched the tip of the spectrum on terrestrial interferometers. And so space-based detectors would also map out new parts of the spectrum, bringing in more interesting data, which will reveal more science and a new understanding of the. Thank you. Let me stop there and field a few questions.
Yeah. Thank you, sir, for your talk. I'll take a few questions from here. So first one, Ayush Mishra asks, are there any applications of quantum information science to gravitational astronomy? Oh, you're muted.
Sorry. So quantum information science, I'm not very sure. Probably I can pass on this question to colleagues who work on that. But quantum technology, definitely. For example, if you want to go below the noise, you have to build a squeeze light source, which essentially is a kind of a light source where you trade the noise between the phase part and the amplitude part, so that you can improve the sensitivity below the short noise. So that's a quantum technology. It's not quantum information technology, but essentially it uses the quantization of fields to do that. The coatings are also driven by the Brownian noise, which is the understanding of how the phononic distribution of noise happens in the coating. So there's a quantum metrology part of the quantum technology that influences and impacts gravitational detectors. And one can claim probably the LIGO detectors are the first applied use of quantum metrology to do actual use of quantum techniques to do measurements.
Next question I take from Krishnan. He asks, any significance in having LIGO India at Anudha, gravitational wave, latitude, longitude, or of the location?
Yeah, so the site was primarily chosen. There is always a benefit of choosing a place which can form the largest possible triangle. But given the Earth size and the relative size of the Indian peninsula, that advantage is not much. So the primary driving motive was to get the lowest noise for the ground motion. So among the various sites that were detected, the primary driving motive was to find the site which has a lower seismic noise so that you can have the highest possible sensitivity. So that's how we ended up in the Deccan Plateau. And the triangular growth, for example, from the Deccan Plateau, if you move up to Madhya Pradesh or move down to Karnataka, the size of the triangle that you form between the three LIGO detectors does not change very appreciably. But the site noise does change appreciably. So the main motivation was the seismic noise of the site. And the Deccan Plateau is a very old geological formation. So we hardly see any ground motion or micro earthquakes or microseismic noise there.
Next, I take Sandeep's question. I was studying nonlinear memory effects of gravitational waves. Since several gravitational waves would be passing through the LIGO, do these gravitational waves leave permanent cumulative change in the LIGO arm length, like like a gravitational wave memory? Does the memory effect depend on the gravitational wave source, or is always occurring? Are design and engineering changes being considered for measuring the gravitational wave memory by Advanced LIGO
Sure.
or
Yeah.
the future versions?
So let me put it this way. So effectively, when the gravitational wave passes through interferometer detector, the mirrors are not primarily moving in the sense. The space between the mirror and the beam splitter themselves are undergoing elongation and compression. In some sense, the metric itself is being modulated. So what the mirrors are working as are time as distant posts to measure the distance between the mirror and the beam splitter. So there's hardly any memory effect in that sense of in the detector. And in fact, it is plagued by a lot of noise that you want to maintain the detector in the operating mode. So that's not something that, at least at the current detector level, you are worrying about. You're more worrying about Newtonian noise because of changing air pressure, the effective change of water columns in the body. So that is the first stage that we have to correct for. When the sensitivity is improved, the Newtonian noise is going to be the one that's going to affect our ability to sense better than what we are currently doing.
Next, I take Aniruddha's question. Does gravitational waves have any effect on L points?
On
L points.
what are L points? Lagrange points? Yeah, but see, the amount of effect of gravitational waves on the Earth are so minuscule. As I said, a meter changes by something like 10 power minus 23. So if you're talking about the Lagrange points of the Earth Moon system and the Sun system, I think it'll be hard. It'll be difficult to find them among the various noises of the perturbations in the Earth orbits and the Moon orbits. I'm presuming that when you say L points, these are Lagrange points that you're talking about.
Yeah, it was. Okay, next I take another question. Are there research opportunities or internships for undergraduate physics students?
Lots of them. So there's a within the LIGO project, there is a scheme of things that is built to train people at various levels. There are projects at the MSc level that we handle at IUCA, Arakat, and other places. We'll be happy to have people who would like to do a one-year MTech programs project also. For example, we have a understanding with LIGO, with IIT Indore, where we run a course on advanced lasers and optics, where the MTech project is done at Arakat in LIGO-related activities. MSc projects are something that IUCA has set up various labs to do short-term projects of 3 months and 6 months. There are projects which people may want to do at BTech level in summer programs. So there are various levels of doing projects, and we'll share those information as we move forward. Apart from that, we have extramural funding. The lead agencies are not the only expertise building effort. There are extramural fundings from the LIGO project, which will allow any university or any college in India to participate in the experimental activities of LIGO India. And these call for will be issued shortly in the later part of April.
There is one more question from Anuruddha. He asks, how would lightning affect interferometer?
Yes, so I did not touch on what is called the physical environment monitoring system. As I said, if the air pressure changes, there's a Newtonian noise change. So similarly, electromagnetic interference matters a lot. Fortunately, the interferometer and optics sits inside metal tubes, so that is isolated to a large extent. But Schumann resonances, lightning can produce effects. So we have what is called a physical environment monitoring system, which is a collection of various detectors, mainly seismometers, barometers, geophones, and then EMI sensors, weather station data, and everything, which is used as the PEM channel. So any data that the LIGO detectors collect are checked against the PEM channel to see the sanctity of the detector is maintained, and those portions which are corrupted because of general noise are discarded. They are not considered for this one. Yeah. So the detector has an uptime of something like 80 to 80% in terms of the data. And many a times you may have earthquakes which distorts your signal, because even though you have isolation of 10 power 14, 10 power 15, earthquakes will get through because you have accounted for 10 power minus 9 kind of a motion on the earth, but earthquakes can produce sizably large. So those environmental factors which destroy sensitivities, that portion of the data are kind of discarded from the PM channel triggers.
Okay, we'll take one more question from Sandeep. Sandeep is asking, is quantum squeezing implemented in 10 meter prototype?
Not yet. So that's the first test bench that we'll be using. So the 10 meter serves multiple test benches. So currently it is in a configuration called C1, which is being used by the controls engineering team to learn how to do suspended interferometer. So currently it will be transferred to a Fabry-Piro-based Michelson interferometer, which will make controls at almost same. Concomitantly, the 5 dB squeezing light source is completed. We'll be kind of putting it into a control rack which can go to the 10 meter. So next year is when we'll be implementing squeezing in the Fabry-Piro Michelson interferometer in the 10 meter. And if you would want to be part of that, you're welcome to join the team to do that part.
How much can we rely on channel? Anuruddha asks this. So is it a part of another question?
I didn't catch the import of the question. Can you?
Yeah. The question is how much can we rely on channel? So I don't know. Regarding the
PM channel? Yeah. So if you're referring to the PM channel, yes, the PM channels are quite robust. But in spite of that, you would want to make sure that the events are of similar templates from all 3 detectors. See, obviously, the 2 detectors in the US are separated by 3,000 kilometers. On the Indian side, they're separated by a factor of another 10,000 kilometers. So if you have a template match detection in all the 3 detectors, it's very unlikely that they are local events. It has to be global events. But then even then, you still look at the PM channels. So there is always a chance of detecting something which is not astrophysical, but then that is the possibilities or the probabilities are very, very low because the PM channels are used to flag. And then you do template matching to look at it. And all 3 detectors have to have, if they have similar sensitivities, then they are all looked at in coherent fashion. So that's the advantage of that.
Yeah, there is one more question from Sandeep. Why is the 4 kilometer maximum length?
Yeah, so 4 kilometers is a kind of a trade-off based on the curvature of the Earth. It's an engineering limit. So you'll appreciate that the Earth, as you move around, the Earth curves. So the mirrors that are suspended from suspensions are hanging from this suspension. So at 4 kilometer length, they'll not hang vertical, they'll hang at a certain angle. So the amount of energy or the amount of actuations at that point which was used was based on electrostatic actuation. So it came from the engineering limits at this point. There is no intrinsic physics limit to the 4 kilometer. In fact, the next generation detectors are being planned are more like tens of kilometers, and 40 kilometers and 20 kilometer kind of designs, where the actuations have to be reworked out and they have to be worked out. But the LIGO design was kind of a trade-off between the sensitivity versus what is actuatable. So the 4 kilometer comes from that limit.
Yeah, we have got one more question. Yeah. So what is gravitational wave modulation?
Gravitational wave modulation or gravitational wave astronomy, I think. Modulation would be, I would say that the arms are modulated by the passing gravitational wave. So you get the imprint of the gravitational wave on the light done, and then that is how we detect. But if you want to know what is gravitational wave astronomy, so gravitational waves open up a new window of observing the universe, right? Till 2015, the whole universe was observed using only electromagnetic radiation, right? Everything from, let us say, radio waves to X-ray astronomy. Everything is electromagnetic radiation. And electromagnetic radiation is prone to scattering, intermediate absorption between interstellar space, intergalactic space. Gravitational waves are, as I mentioned, space is very, very stiff. They hardly undergo any scatter. So they're very good messengers in terms of understanding binary mergers, and they can arrive unperturbed on Earth, even though they're traveling few billion kilometers and a few billion light years, light years. So they are very good triggers, and this mechanism of looking at the universe in this new window is called gravitational astronomy.
We have 4 more minutes. So then we will take this question. LIGO India is not sensitive enough to detect a stochastic gravitational wave background, right? So only hope is Einstein telescope or cosmic explorer.
See, even cosmic, no. LIGO detectors are not sensitive enough for microwave background. The gravitational background is fine, but there are many techniques that allow you to kind of look at an estimate on the excess power. So people see, scientists are very ingenious people, so they try to make do with what is available. So people do in the LIGO science collaboration try to estimate what could be the excessive power and put upper limits on this contribution from the stochastic background. Yes, as sensitivities of gravitational waves improve with Cosmic Explorer, Einstein telescopes, and further, you have better chance of detecting them and not just putting limits. So I agree there. Yeah.
Mm. Okay, what about space-based interferometer? How would it help you?
So the most promising one is LISA, as you saw in one of the slides. On the Earth, you cannot hope to detect anything below 10 hertz. There is a wall of seismic noise in the 2 hertz, 0.2 hertz band. So anything that you want to detect below 1 hertz in the decihertz band or millihertz band or nanohertz band, you have to go to space. So LISA is one such example. It's slated to fly in the later part of in the early part of next decade, and that will look at millihertz, nanohertz kind of gravitational events from supermassive black hole mergers. We are also in a very nascent phase of trying to propose a LIGO in sky kind of a detector, which is for decihertz, so that we can do what is called multi-band gravitational wave, so that the decihertz band of the detector in space in Earth orbit and LIGO can merge as a single entity, working from decihertz to kilohertz kind of a band. But that's in a very early stage of proposals. So.
Is the modulation also about sidebands and generation and side?
The gravitational wave do not directly produce the sidebands, but we do introduce sidebands to have control channels for aligning the interferometer. So I did not show you the control mechanism at all. I just showed you a very simplistic picture of the interferometer. But to align all the interferometers and to maintain the arm length to nanometer accuracy, you need to kind of have sidebands so that you can use them to do the modulation and correction for that. So we have acoustic modulators and other things which introduce intentionally the sideband, so that you can use them as control features on the interferometer fabric probes and the other part of that.
How are particular wavelength of lasers equipped in LIGO after LIGO effect detection of gravitational waves?
Yeah, in the first order, it does not, the wavelength is not very sensitive, simply because the Michelson interferometer is a kind of a balanced interferometer. The two arms are almost of similar length. So lambda does not play a role except for a factor of 5, because the amount of quadrature that you acquire, you multiply by lambda to get the actual displacement. So it works like a scale factor. But the choice of wavelength that was done was based on the laser technology available. So if you want to build very narrow line width of hundreds of watt of power, NDAG was the only laser system that could allow you to do that at that time. So that was what was chosen. So 1 micron comes from the choice of the laser, which can achieve the required narrow line width and still go to powers of few hundred watts.
So with this, we will close our talk. So once again, I thank Dr. Sendhil Raja for the wonderful talk and also patiently answering all the questions, and also all the viewers joining us, and stay updated for our upcoming talks. And yeah, subscribe to our mailing list and join our social media. I mean, you will get updates about upcoming events from ICTS. Thank you. Thank you, all of you.
Thank you. And thank you for this opportunity to be able to talk about LIGO India project to all the young colleagues who probably will become the next generation of people who use this facility.